Hey folks, welcome to your first set of AP Chemistry video notes. The first unit in AP Chemistry is all about atomic structure. We're going to cover the first 4 topics in this unit today. Years from now, when you've forgotten most of the chemistry you learned in high school, my goal is for you to remember that the mole allows us to compare different units. Topics 1.1 through 1.4 ask you to calculate the quantities of a substance or its relative number of particles using dimensional analysis in the mole concept, explain the quantitative relationship between the mass spectrum of an element and masses of the element's isotopes, explain the quantitative relationship between the elemental composition by mass and the empirical formula of a pure substance, and explain the quantitative relationship between the elemental composition by mass and the composition of substances in a mixture. That's a lot to cover, so let's get started. Unfortunately, we do not have the ability to count individual particles when we're performing lab work, but we can measure the mass of our reactants. If only there were a way to relate the mass of a reactant to the number of particles of that reactant. Well, lucky for you, there is. Sort of. We can't directly relate mass to the number of particles, but we can relate the number of particles to the number of moles, and then relate the number of moles to the mass. There's 2 important pieces of information we need to make these conversions: Avogadro's number and the molar mass of your substance. Avogadro's number is 6.022 times 10 to the 23rd power, with a unit of per mole. This tells you how many atoms, molecules, particles, or whatever is in 1 mole of any pure substance. We often express the mass of a single atom in atomic mass units, or AMUs. That's pretty useful to us because the average mass in atomic mass units of 1 particle, or formula unit, will always be numerically equivalent to the molar mass of that substance. For example, 1 atom of oxygen is said to have a mass of about 16 atomic mass units. If we had 6.022 times 10 to the 23 atoms of oxygen, or 1 mole of oxygen, it would have a mass of 16 grams. When doing stoichiometry before, you may have used a mole map similar to the one here on my left. You'll need to be able to perform these calculations without looking at the mole map when it comes to the AP exam. Let's do an example. So our example says that a student is given 50.0 liters of an unknown concentration of sodium carbonate solution. The student mixes it with an excess of 1 molar calcium nitrate solution, forming a precipitate of calcium carbonate according to this reaction. The student filters and dries the precipitate and finds the mass to be 0.93 grams. So for question A, it wants to know how many moles of sodium carbonate are present in the original solution. To do this, we need to know how many moles of calcium carbonate were produced. To find that, you take your 0.93 grams of calcium carbonate and use the molar mass as a conversion factor. So to do that, you'd have to know the molar mass of calcium carbonate. According to our periodic table, calcium has a mass of 40.08 grams per mole. Carbon has a mass of 12.01 grams per mole, and oxygen has a molar mass of 16.00 grams per mole. But there are 3 oxygens, so we have to multiply this one by 3. So 3 times 16 is 48. Add them all up and you get 100.09 grams per mole. But all of these have 4 sig figs, so it's actually 100.1 grams per mole. That means that there are 100.1 grams in every 1 mole of CaCO3. And this would get you right now to moles of CaCO3. But since you know stoichiometry, you could just continue on because we're looking for moles of Na2CO3. According to our equation, for every 1 mole of CaCO3, we had to use 1 mole of Na2CO3. So when you multiply the tops and divide by the bottoms, you get that our original solution must have had 0.0093 grams per mole. Why 2 sig figs? Because we have 2 sig figs over here. So that's part A. I'm going to get rid of all this now so we can move on to part B. A rookie mistake, I didn't go through and cancel my units. That is not grams per mole. You probably caught that. It's actually just moles. So part B wants to know how many particles of Na2CO3 that we had in our original solution. To do that, we have to use Avogadro's number to convert from moles to particles. So we take our 0.0093 moles of Na2CO3, multiply that by, according to Avogadro, there's 1 mole for every 6.022 times 10 to the 23 particles. And when we multiply those, we get 5.6 times 10 to the 21 particles of Na2CO3. Part C wants to know how many atoms of carbon there were. So we look at, there's 5.6 times 10 to the 21 particles of Na2CO3. And for every 1 particle of Na2CO3, we have 1 carbon atom. So that answer would be the same. There are 5.6 times 10 to the 21 particles of carbon. And lastly, for part D, do the same for sodium. So if there's 5.6 times 10 to the 21 particles of Na2CO3, pardon my handwriting, Na2CO3, for every 1 of these, there are 2 NAs, so 2 particles, atoms, of Na for every 1 particle of Na2CO3, which gives us an answer when we multiply that of 1.1 times 10 to the 22 particles. I would make sure you know how to do significant figures and that your answers are reported to the correct number of significant figures, because it seems like they tend to care about that on the AP exam. You should already know how to do these kinds of calculations based on your experiences in both Chem 1 and Chem 2 the last 2 years. That said, if you're unsure about your ability to firmly say you can do any of these 4 things, please let me know so I can help you out. Topic 1.2 is all about mass spectroscopy, something that's probably very new to you. You should already know that each element exists in multiple forms called isotopes. Isotopes of an element have the same number of protons, making them the same element, but have different numbers of neutrons, giving them different masses. Without going into extraneous detail on how a mass spectrometer works, basically it takes a small sample of a substance and shoots electrons at it in order to ionize the particles, giving them a charge. Then it accelerates the particles, pushing them past an electromagnet that's generating a magnetic field. As the particles pass through the magnetic field, they get deflected at different angles due to their different charges and masses. And finally, they land on a detector that measures how many particles hit in different spots. By the end of the process, you get a graph that looks like this, where the masses of each isotope are on the x-axis, and the relative abundance of each isotope is on the y-axis. That's the part that's probably new to you. Once you have the mass and natural abundance of each isotope, you should know how to calculate the average atomic mass of the element, the mass we have on the periodic table. In case you've forgotten though, here's a quick rundown. To find the average atomic mass, you take the mass of one isotope and multiply it by its percent abundance. Then you take the mass of another isotope and multiply it by its percent abundance, and keep doing this until you've multiplied the mass and percent abundance for each isotope. Then you add up all of those products and you'll have the average atomic mass. So let's try an example. Okay, this question asks us to calculate the average atomic mass of the following element based on its mass spectrum, and then determine what element it is. As we said earlier, you need to know the masses and the relative abundance of each isotope in order to find the average atomic mass, and we can find those by reading the mass spectrum. When you do this on the AP exam, you might see a graph similar to this. You may notice that it's not exactly super easy to read, and different students might read it slightly differently. The AP exam usually accounts for that and allows for a certain margin of error, so do your best to estimate on these. Now, this graph gives us the relative abundance of two different isotopes. These isotopes look to have a mass of about 10 and 11, but the relative abundances are around 25 and 100 respectively. This is a relative abundance, not a percent abundance. You'll have to determine the percent abundance on your own. So if the isotope that weighs 10 has 25 out of a total of 125 atoms, that's a percent abundance of 20%, or 0.2. Isotope 11 is 100 out of 125, which is 80%, or about 0.8. If all of the peaks on your graph added up to 100, you'd be able to skip this step because that would come out the same as the percent abundance. Now we can move on calculating the average atomic mass. You take your 10 times 0.2 or 20% and 11 times 0.8 or 80% and find those products, which gives us 2 and 8.8. Then you add those products up and you get 10.8. So the average atomic mass of this element is 10.8 AMU. Now, part B of this question asks you to identify what element that is on the periodic table. So grab your periodic table and find which element has an average atomic mass of 10.8. That looks to be boron. Again, if you have any issues with either of these I can statements, please let me know. I'll help you turn your I can't into an I can. Next up is topic 1.3, elemental composition of pure substances. Some pure substances consist of individual molecules. Others consist of atoms or ions held together in fixed proportions, described by a formula unit. For example, table salt always consists of a ratio of 1 sodium ion to 1 chlorine ion, but they're not part of distinct molecular units. They're part of a crystalline structure. Either way, both of these types of pure substances follow the law of definite proportions, which says that the ratio of masses of constituent elements in a pure substance is always the same, regardless of the sample size. This leads us to the empirical formula, which is nothing more than the simplest whole number ratio of atoms or elements in a compound. We'll talk more about this later on, but a molecular formula expresses the actual number of atoms in a covalently bonded molecule, not just the simplest ratio. The percent composition of anything can be described as the mass of one part divided by the total mass of the whole substance. Let's do an example of this. This question tells us that a sample of pure compound consists of 5.81 grams of carbon, 1.46 grams of hydrogen, and 7.73 grams of oxygen. It asks you to first find the percent composition of each element in this compound. To do this, you'd have to find the total mass by adding up all the masses you're given. If you add these up, you should get 15 grams for your total mass. Then you divide each individual mass by the total. This gives us 5.81 divided by 15 for carbon, 1.46 divided by 15 for hydrogen, and 7.73 divided by 15 for oxygen. When we divide those out, we get 0.3871, or 38.71% for carbon, 0.0974 for hydrogen, or 9.74%, and 0.5155 for oxygen, or 51.55%. Next, the question asks you to find the empirical formula for this compound. There are a couple ways we could do this depending on what your first question was here. If you didn't have to find the percent composition, you could just divide each given mass by the respective element's molar mass to get the molar ratio of each element. This would give us 5.81 divided by 12.01 for carbon, 1.46 divided by 1.008 for hydrogen, and 7.73 divided by 16.00 for oxygen. This will give us molar ratios of 0.484 for carbon, 1.45 for hydrogen, and 0.48 for oxygen. Now, since the empirical formula is the simplest whole number ratio of the atoms, we have to get these into whole numbers. So to do that, divide by the smallest you have here, so divide each one by 0.48, and then when you find your answers, round to the nearest whole number. So that gives us ratios of 1, 3, and 1, giving us an empirical formula of CH3O, 1 carbon, 3 hydrogens, and 1 oxygen. Now, FYI, we could have done this with the percent compositions as well, since the law of definite proportions tells us that no matter the sample size, the molar ratio is going to be the same. We could use those percents that we had before and just make it out of 100 grams. So we could use 38.71 grams instead of percent, 9.74 grams, and 51.55 grams. This would take the place of this step here. The rest of this is going to look exactly the same. So divide by 12.01 for carbon, divide by 1.008 for hydrogen, and divide by 16 for oxygen. And you get molar ratios of 3.22, 9.66, and 3.22. Then divide by the smallest number again, so divide each one by 3.22. And you still get 1, 3, and 1, the same empirical formula. Lastly, and I'll just squeeze this on the bottom here, the problem asks us to find the molecular formula if our molar mass for the compound is 62.07 grams per mole. To do that, we have to know the molar mass of our empirical formula, so we've got 12.011 for carbon, 3 hydrogens, so 3 times 1.008, and 16 for oxygen. When we do that math and add it all up, we get a molar mass of 31.03 grams per mole for CH3O. Now you take your actual molar mass, the 62.07 grams per mole, and divide by your empirical molar mass, so 31.03 grams per mole, and you get it to be about 2. That means that your molecular formula is actually twice your empirical. So instead of CH3O, the molecular formula would be C2H6O2. If any of these statements are I can't statements for you, come ask me for help. Last but not least, on to topic 1.4, the composition of mixtures. The 2 important things you need to know from this topic are that mixtures do not follow the law of definite proportions, therefore they can consist of varying ratios of elements, molecules, or formula units, and that we can perform an analysis on mixtures to determine the relative number of atoms in a sample and determine its purity based on that. There's no new equation for this one. Our percent composition equation is the same. We just have to shift our mindset to get out of the realm of fixed proportions and think about how the percent compositions could be affected by having different types of mixtures. So, for example, you have a solid that you know is mostly sodium chloride. You suspect it may also contain sodium iodide, potassium chloride, or lithium chloride as well. When you analyze the sample, you find that it contains 73% chlorine by mass. Is that sample a pure substance? And if not, what other substance is it likely mixed with? Let's do that example on the board. So the first step to solving this problem would be to find the percent composition of chlorine in sodium chloride. If that matches up with our 73% analysis, it's likely pure NaCl. Try this out on your own and resume the video when you're ready to check your answer. Okay, so we took the molar mass of chlorine, 35.45, and divided by the total molar mass of sodium chloride, which would be 22.99 plus 35.45. And when you do that, you get a percent composition of 60.66% chlorine by mass. So 60.66% is not very close to 73 at all. So I would say that our substance is not pure sodium chloride. Let's find the percent compositions of the other three substances that we think might be mixed with our sodium chloride. First up is sodium iodide. There's no chlorine in sodium iodide, so it has a 0% composition. If the percent composition of chlorine is supposed to be 60.66, and we mixed it with something that had 0% chlorine in it, that would bring our number down. So this must not be our culprit because our number was higher. It was 73 instead of less than 60.66. Next up is potassium chloride. Do this the same way you did up here. You have 35.45 for chlorine divided by 39.10 for potassium and 35.45 for chlorine. That gets us a percent composition of about 47.55%. You actually probably didn't have to punch that in the calculator if you're worried for time, because you recognize that this denominator is bigger than this denominator, which means this number would be smaller. And if it's smaller, it's going to bring this number down, but instead we had 73, so our number was higher. So potassium chloride is also not our culprit. Lastly, we have lithium chloride. Do this one the same way, 35.45. Lithium is only 6.94 grams per mole. And you can already tell, since this denominator is much smaller than this denominator, this answer should be much higher. In fact, it comes out to 83.63%. Since this number is higher than this one when we average them together or mix them together, then our percent chlorine would increase. So lithium chloride is probably our culprit. It's probably what our sodium chloride is mixed with, making it no longer a pure substance, but a mixture. Here are your last set of I can statements. You know the drill. I hope this lesson has helped to get you jump started on your way to preparing for the AP exam. We'll practice these skills in class in various ways so that you're prepared to use them in any way the AP exam might ask you to. As always, if you have any questions, let me know.